Good evening, students. Prustis are back again today with a new topic, that is self-inductance calculation. So, all of you must have studied in the electromagnetism the self-inductance of coils, which is a geometric parameter. To calculate that, we use certain method like flux enclosed by current, but there is some common error we will discuss today. This is my credential as always, you see. So let's calculate self-inductance of a coil carrying current I. See this diagram. Even if it doesn't carry the current, its self-inductance will be there because it's a geometric parameter. To calculate self-inductance, we may have to pass current, measure flux, and take the ratio. That's what we do, similar to the capacitor. Capacitance of a capacitor does not depend on whether it has charge or is not, it is uncharged. But to measure that, we may have to give charge on the corresponding potential rise and take the ratio of charge divided by that potential rise. For the measurement purpose, we may have to give some charge. Similarly, to measure the self-inductance of this coil, we may have to pass current I, and this is thin wire. See, this thin wire is very important. This is thin wire. Means the diameter of the wire is negligibly small, and the magnetic flux passing enclosed within this loop are shown by arrow mark. So the diameter of the wire through which the current I flows is very small, thin wire. We measure the magnetic flux enclosed in the area bounded by the current carrying wire loop. See the figure 1. Since the diameter of the wire is negligible compared to the area of the loop, the overlapping area, so if I ask you what is the overlapping area of the flux and the current, negligibly small, because the area of the current flow itself is very, very small, because the thickness of the wire is very small. That's what I am saying. The area of the overlap, area of the loop, area of the overlapping area of the magnetic flux and the current in the wire is negligibly small. So magnetic flux region and current region, they are having negligible small overlapping area. We therefore say the total magnetic flux is enclosed within the current carrying loop. Okay? That is, we say the total magnetic flux is enclosed within the current carrying loop, enclosed by a negligible diameter wire. That loop is enclosed by a negligible diameter wire, current carrying wire. The self-inductance is defined as flux by I. L is the self-inductance. I is the magnetic flux enclosed within the loop. I is the current in the wire forming the boundary of the loop. I is what? Current in that wire. The wire is forming the boundary of the loop, and wire diameter is negligibly small. So there is no or negligible overlapping between the flux area and the current area. Current area is what? Current area is just the diameter of the loop. This thickness of the loop is the thickness of the wire is the current area. See, thickness is negligibly small, so current area is negligibly small. So overlapping area of the flux may pass through the wire, but wire thickness, but that area of overlapping how much? Negligibly small, because that area of the current flow itself is negligibly small. You know? Right? But whereas the area of the loop, or the area through which the flux passes is quite sizable. But the overlapping area between the flux and the current carrying wire, current region and flux region, the overlapping area, the common area is negligibly small. So in that case, I can use flux by I. And all of you know this unit of self-inductance L, that is Henry. Now let us make, see better I write, let's make the diameter of the wire of sizable size. Or is it that maybe let us make the diameter of area sizable. Area large. So diameter of the wire, make it large now. See the diagram. This is the wire now. Wire cross section area is this. That loop I marked here. Na? This is the cross section area of the current carrying wire. So earlier it was just a line because the diameter was extremely small. Now the diameter of the wire is quite large. Yes or no? This is the diameter of the wire. This is the diameter of the wire. Diameter of the wire. Quite large now. It is not negligibly small. So the current region, current area is no longer negligible. And the flux, as you can see, passes through the inside area as well as through the body of the wire also, like this. The red lines, magnetic flux. Okay. As you see in the figure 2 here, there is a sizable area of overlap. Sizable area overlap is there between the current and the flux. Okay. So sizable overlap, I'll write it. Sizable overlap between the flux area and the current area. So as you see here, the boundary around the total flux, just see, the total flux will be throughout this inside as well as this in the thickness of the wire. Also the flux will be there. So total flux is bounded by this outer line, but the total current is not passed by the outer line only. Total current passes through the whole thickness of the wire. But the total flux is not enclosed by the total current. The total flux will be enclosed by the outer line, but outer line does not carry the total current. And if you say the inside area flux, that is bounded by total current, but that is not the total flux. That is inside area flux is not the total flux, even if it is bounded by the total current. And the total flux is bounded by just an outer line, but outer line doesn't carry total current. So very difficult to find the proper contour here so that we can use flux by total current. So since the overlap between the flux area and the current area, the flux area and the current area, since the overlap between the flux area and the current area, there is a sizable overlap between flux area and the current area. As you see here, the boundary around the total flux doesn't carry the total current. I just explained it. So the L is equal to total flux divided by total current enclosing the total flux. I cannot apply because the total current is enclosing only the inside area flux, not the total flux. So this relationship I cannot apply, is not applicable. Am I clear? So this is applicable only when there is overlapping between the current area and the magnetic flux area is negligible. But here in this case, it is not so. The current area is, because a thick wire, so current area and the magnetic flux area overlapping part is not negligible. So which current is overlapping the total flux, or the total current is overlapping which flux? They are two different things. So it is very difficult to apply. It's in this case impossible to apply total magnetic flux divided by total current enclosing the total flux. Okay, the total current, if it is I is not enclosed, it is distributed over the cross section. So that means the total current I is enclosing only the inner flux. But if I consider the flux through the inner as well as this flux in the current area, then the total current is not enclosing this total flux. This total flux is enclosed only by the outer line, but outer line does not carry the total current. Understood this? So it is, this relationship is not applicable. Then कैसे calculate करेंगे भाई self inductance? ये अब केस में जहां पर कि जो overlapping area है negligible नहीं है between current and the magnetic flux, the overlapping area is not negligible. आपको ये मालूम होगा UM, that is energy per unit volume, energy density in the magnetic field, we get as B square by 2 mu naught in free space. You know this energy density, joules per meter cube, where UM is energy density, B is the magnetic field at a point in space, mu naught is magnetic permeability of free space. This is a point-to-point relationship. We call this local relationship. Total current will be, this is per unit volume, multiply d volume of a small elemental region and integrate. So that's what U, d volume integration. That will give you the total energy, that is B square by 2 mu naught d volume integration. Okay. Over what region this has to be performed? Wherever there is B. So it has to be performed over the region of magnetic field. Okay. U is the total energy. Remember this. We do not have to bother about the contour or the boundary like in the case of the L is equal to 5 by I. जो boundary हमको चाहिए वो सब कुछ जरूरत नहीं, इधर सीधा इंटीग्रेट करेंगे B square by 2 mu naught d volume wherever B is present, the whole region of B. Okay. And you also, you know, the total energy is, if L is the self-inductance, then total energy of the coil will be half L into current square, I square. So equation 3 and equation 4, they are the expression of same physical quantity called total energy. So equate them. So 1 by 2 mu naught integration of B square d volume is equal to half Li square. Half cancels from both sides. So what is L? B square d volume integration over the whole space having magnetic field divided by mu naught into current square. This is the equation 5. That is the general expression of self-inductance. So this gives a more accurate value of the self-inductance cell, because here we are not bounded by we are not very much bothered about the which boundary contains how much flux or which current boundary contains how much flux. We are not bothered about all that. Okay. So note मैंने लिखा, we can use equation 1, that is L is equal to flux by I, only when the overlap between the flux and the current is negligible. तो एक एग्जांपल देंगे, पेज 2 में जाएंगे. अभी आपको समझ में आ गया ये चीज? तो कैसे करेंगे, how to determine L value more accurately? We'll be using this expression. This is quite elegant expression, equation 1, but that can be used only when the current region and the magnetic flux region, overlapping is negligible. This is not explicitly written in our books, so be very careful here. We go to the next page. So next page अभी आगे ले लो, आ गया नेक्स्ट पेज. एग्जाम्पल लेंगे इसमें. एग्जाम्पल ये है, a long conducting solid cylinder, long cylinder of radius small a is coaxial with a thin long conducting jacket of radius b greater than a. Find the self inductance L, that is value of this geometrical arrangement for the current flow along the length of this cylinder and the reverse current flowing through the walls of the jacket. This is the jacket. ये लिख देंगे भाई, ये जैकेट है. ये है आपका जैकेट. ये है conducting body. This radius A, just see this diagram. You see a gray color solid cylinder, that is the inner cylinder carrying current I. Capital I is the current, and the same I is returning back after a long distance, is turning back through the jacket. So all of you must be knowing, I am not discussing that. The B inside 0 to A, when R is radius is from 0 to A, there is B inside, concentric B, and between radius A to radius B also concentric B. Their expressions will be different, but both the places the field will be concentric, as I have shown in these concentric circles. And outside the B, outside the jacket, there will not be any magnetic field. क्यों भाई? Apply Ampere's law, take a loop outside. B dot dl integration will be into 2 pi r is equal to mu naught I enclosed. But I enclosed 0 because I going up and I coming down. So net I is 0. So mu naught I enclosed is 0. So B into 2 pi r is 0. So B outside will be 0. That you know. Let these things I think you know. That's why I'm not writing explicitly. So पहले मेथड 1 में phi by I में मेथड में करेंगे. मैं बोलता हूं कि इसमें आपको गलत आंसर आएगा. क्यों आएगा? क्योंकि ये जो इनसाइड दिस सॉलिड सिलेंडर देयर इज करंट रीजन and the flux also they are existing in the same area. Yes or no? In the gap between the cylinder and the jacket, there is no current, only B. So no problem here. Applying L is equal to flux by, that is L is equal to flux by I. But here, if I apply L is equal to flux by I, that will give me an inaccurate result. So the whole total L, that is flux by I cannot use that expression because a part of the region there is a overlapping between the flux and the current. From 0 to A, the current region, current flowing through that, and also magnetic field existing in that region. So current region, flux region overlapping. So that gives an inaccurate result. Let us apply that inaccurate method and find out. So magnetic field B will be concentric rings. So what is the flux through this rectangular area? Flux will be through this rectangular area plus this rectangular area. This rectangular area from 0 to A and the outside rectangular area from A to B, and there is no B outside. So in calculating the magnetic flux phi 1 inside the cylinder, R 0 to A के बीच में. So B क्या होगा भाई? R, if R is within this solid cylinder, mu naught I small r divided by 2 pi a square. ये आपको मालूम होगा जरूर. B of a solid cylinder, current carrying cylinder, quite long, infinite long. The direction is, that is the circulating magnetic field, so tangential direction. So then take a thin area here. That area will be, dr is thickness, L is the length, so LDR is the area, and B into LDR is the flux through this region. So total 0 to A region, what is the flux in this rectangular region? This B into LDR. That's what I wrote. Mu naught IR by 2 pi S square into LDR. Mu naught IL by 2 pi S square is a constant term into RDR. Then integrate करो phi 1 के लिए. Mu naught IL by 2 pi R square, 2 pi A square, RDR integration 0 to A. So ये होगा A square by 2. A square cancel, it becomes 4 pi. Mu naught IL by 4 pi. Okay, this is the flux through the area inside this cylinder. Now between cylinder and jacket, same, another thin area you take here, but here B expression is different. What is the B expression here? Mu naught I by 2 pi small r. That R is between A to B. And theta cap, same tangential direction. Normal area normal to that is LDR. Just like that, here this thickness, blue shaded, that is also length L and thickness dr. Yes or no? Here, see here, length L, thickness dr. LDR is the area. This is between A to B region, between this cylinder and the jacket. हो गया? So B, this much, mu naught I by 2 pi R, and a thin area is LDR. So deep flux will be B dot dA, that is BdA, that is mu naught I by 2 pi R LDR, mu naught IL by 2 pi dr by A. Now what is the total flux between A to B, between the gap, in the gap between the cylinder and jacket? Integrate this. This is constant. dr by R integration A to B is ln B by A. So this is the phi 2. Then what is the total flux through this area from A to B, 0 to B? The flux 1 plus flux 2. The total flux will be B is equal to 0 at R greater than B, applying amperes, like I told you earlier. So total flux enclosed within the geometry is how much? Flux 1 plus flux 2. Mu naught IL common ले लो. Mu naught IL by 2 pi common ले लो. So half रहेगा phi 1 से, and ln plus B by A रहेगा phi 2 से. So phi 1 plus phi 2, mu naught IL by 2 pi, half plus ln B by A. And L will be flux by I. So mu naught L by 2 pi, half plus ln B by A. ये आपका आ गया. जो L, due to that inaccurate method, because why inaccurate I told, because there is a overlapping. Still I am using flux by I method. So method 2, B square d volume integration by mu naught I square is L method, that one. Equation 5 in the page 1. Refer to the above diagram, same diagram refer करो. B तो you know, between 0 to A, B you already know, mu naught capital I small r divided by 2 pi S square. Okay. D volume how much? ये जो अभी देखो ये डायग्राम क्लोज देखो, ये जो B है it passing through the thin cylindrical cell. इधर B कितना है? mu naught I small r by 2 pi A square. Then what is the volume of the cylindrical cell? 2 pi r dr into length, है ना? So ये volume में total energy how much will be in that thin volume? How much there? B square by 2 mu naught into this volume of the thin cylindrical cell. बस हो गया, ये मैं वही लिख दिया. So B square d volume का जो इंटीग्रेशन है, that is mu naught square I square R square by 4 pi square A4, ये B square into d volume is 2 pi L R dr, 2 pi R dr L. Okay, so उसका इंटीग्रेट करो. हमको चाहिए ना, उसका इंटीग्रेशन चाहिए, ये मेथड टू इसका ये इंटीग्रेशन करके डिवाइडेड बाई म्यू नॉट आई स्क्वायर करने से एल निकलेगा। सो उसका पहले न्यूमरेटर वैल्यू हम निकालेंगे, बी स्क्वायर डी वॉल्यूम। सो बी स्क्वायर डी वॉल्यूम वैल्यू इन हम 0 टू ए के बीच में क्या आएगा, म्यू नॉट स्क्वायर आई स्क्वायर आर स्क्वायर बाई 4 पाई स्क्वायर ए टू द पावर 4 इंटू 2 पाई एल आर डी आर। 2 पाई कैंसल विथ 4 पाई स्क्वायर, 2 पाई रहेगा, म्यू नॉट स्क्वायर आई स्क्वायर एल आउटसाइड, और नीचे में क्या रहेगा 2 पाई ए फोर्थ, और इनसाइड इंटीग्रेशन साइन क्या रहेगा आर क्यू डी आर 0 टू ए, दैट इज द विदिन द cylinder. So this will be a fourth by 4, that's it, a fourth for cancels. So mu naught square I square L by 8 pi. This is the B square D volume from 0 to A. Then A to B, how much will be B square D volume? B is mu naught I by 2 pi R. ये when it is A to B के बीच में, how much it is? B here is mu naught I by 2 pi small r. But the expression for the thin cylinder volume is 2 pi r dr into L, just like before. So A to B का बीच में I'll again evaluate B square D volume. B is mu naught I by 2 pi r, उसका स्क्वायर हो जाएगा म्यू नॉट स्क्वायर आई स्क्वायर बाई 4 पाई स्क्वायर आर स्क्वायर, डी वॉल्यूम इज 2 पाई आर डी आर एल। सो देन इंटीग्रेट करो बी स्क्वायर डी वॉल्यूम को, क्या क्या बाहर ले आएंगे, म्यू नॉट स्क्वायर आई स्क्वायर बाई इंटू एल बाई 2 पाई, एंड दिस इज डी आर बाई आर इंटीग्रेशन, दैट इज एल एंड बी बाई ए। सो हाउ मच इज बी स्क्वायर डी वॉल्यूम इंटीग्रेशन फ्रॉम ए टू बी, mu naught square I square L by 2 pi ln B by A, equation 6. And R greater than small b, that outside the jacket B is 0, applying ampere, so just before I have discussed. So total B square D volume integration, how much? Wherever B is present, that is inside cylinder as well as in the gap between cylinder and jacket, adding equation 5 and equation 6, this equation V and equation VI. So add karo, you get total value of B square D volume integration, that is mu naught square I square, that is mu naught square I square L by 8 pi plus mu naught square I square L by 2 pi ln B by A. तो क्या कॉमन लेंगे, म्यू नॉट स्क्वायर आई स्क्वायर एल बाई 2 पाई कॉमन ले लेंगे, सो 1 by 4 प्लस एल एन बी बाई ए। देन इक्वेशन 5 जो पेज 1 में है, जो भी हमने लिखा इधर, दिस मेथड 2 बी स्क्वायर डी वॉल्यूम इंटीग्रेशन बाय म्यू नॉट आई स्क्वायर इज द एल, करो बी नॉट टोटल बी नॉट स्क्वायर डी वॉल्यूम इंटीग्रेशन इज दिस मच and divided by mu naught I square. So mu naught I square, if I divide, and I square cancel, one this is the mu naught square, na? Mu naught square I square L by 2 pi 1 by 4 plus ln B by A divided by mu naught I square. I square as cancel, 1 mu naught cancel, so mu naught L by 2 pi 1 by 4 plus ln B by A. ये आ गया आपका L। ये दोनों सेम है क्या, सेम एक्सप्रेशन, ये V I and this IVL, दोनों में डिफरेंस है यही नंबर का, ये हाफ आ रहा, ये तो सेम है, आउटसाइड सेम है। तो फर्स्ट टर्म इन द ब्रैकेट इज 1 by 2 in the inaccurate method, whereas the first term in the bracket is 1 by 4. Other two terms are same, but note that the value of L calculated in two methods are not same, obviously not same. This is 1 by 4 in the second method, 1 by 2 in the first L 5 by I method. As I mentioned, the method 1 gives an inaccurate value of L. L is 5 by I because there is an overlapping of magnetic flux and current regions inside the body of the solid cylinder. So the value of L obtained by method 2 is accurate. We don't care about whether they're overlapping or not, only B square d volume integration by mu naught I square. So that is the correct value of L will be mu naught L by 2 pi 1 by 4 in the bracket 1 by 4 plus ln B by A. That again I am writing here, overemphasizing, this is the answer. L is equal to, again I am saying, flux by I can be used when the overlapping between magnetic flux and current region is 0 or negligible. L will be integration of B square d volume by integration of B naught B square d volume divided by mu naught I square can be used without any restriction. This is the more accurate. This is conditional. Okay. Am I clear? If A is very small, this is just a thin wire, the cylinder radius A tends to 0, just a thin air, very small, then B by A ratio will be quite large. This B by A ratio can be quite large. Okay. So whether it is half or 1 by 4, if ln B by A is much larger, then we can ignore this 1 by 4 or 1 by 2. They will give you similar value. But if A is compared to B, then ln B by A will be small, and this 1 by 4 or 1 by 2, you cannot ignore them. You can ignore 1 by 4 or that 1 by 2 value which I got in this first method, 1 by 2. You can ignore both if ln B by A is very large. Okay. So that's what I am saying. But if A and B are comparable in dimension, then you cannot ignore this first term, and 1 by 4 should be the accurate value, will give you the accurate value of L. Okay. So it is a very conceptual discussion for you. Now you understood when to use L is equal to flux by I and when you cannot use. So suppose you want to calculate the flux of a solenoid, current carrying solenoid. That time you can use flux by I, assuming that the diameter of the wires is very, very small. Understood? Compared to the diameter of the solenoid. So now I think you have understood the whole thing. I'll discuss some more questions in the induction in the coming days. I hope you have enjoyed this class, and all the best for your upcoming examinations. We'll stop here. We'll meet very soon with a new conceptual discussion. Thank you all.